So good evening, everyone. Welcome to the second Haileybury School of Mines guest lecture. This is a lecture series whose purpose is to provide a forum for distinguished members of the mining industry to share their experience with their colleagues around the world. I am Jim Kendall, the program coordinator of the Haileybury School of Mines, which is part of Northern College in Ontario, Canada. It is my pleasure to be your host this evening. I would like to introduce your guest lecturer this evening, Jan van Niekerk, who is the Director of Gold Process Solutions at Metso Outotec in Pretoria, South Africa. Jan will be speaking about the BIOX process that uses bacteria to oxidize ore, which facilitates the extraction of gold and base metals, such as copper and cobalt. Jan's lecture this evening will be in several parts with a question and answer session after each part. Please use the Q&A button on your Zoom toolbar to submit questions by text. I will read your question and Jan will answer. Please note that this guest lecture will be recorded on the Northern College website in the events section. I ask that you please ask questions and conduct yourselves in a polite manner. Impolite behavior will result in suspension of access to the lecture. Jan van Niekerk completed his Bachelor of Engineering degree in metallurgy at the University of Pretoria in 1995. He started his career at GenCore Process Research in 1996, working on the development and testing of the BIOX process. Mr. van Niekerk stayed with the BIOX technology in various capacities until taking over the management of the technology under Goldfields in 2006. Mr. van Niekerk led the management buyout of the technology from Goldfields in 2013 that saw the formation of BioMin South Africa, as well as the subsequent integration of the BIOX process into Metso Outotec. Mr. van Niekerk was involved in the testing, design, and commissioning of a number of BIOX plants, including the Coricancha BIOX plant in Peru and the Fosterville BIOX plant in Australia. Mr. van Niekerk also oversaw the commercialization of the Aster, High-Tech, and BIOX mesotherm processes by the BIOX team. Mr. van Niekerk is now the Director of Gold Process Solutions, looking after the development of the gold hydrometallurgical processes within Metso Outotec. Jan, thank you for sharing your experience with us. Please begin your lecture.
Thank you, Jim. Let me share my screen here. Can you confirm that you can see my screen?
Yes, I can see your screen. Anna, you too? Okay, good. Please proceed.
Thank you, Jim, and thanks for the opportunity to give this lecture. Like I said, my lecture will focus on the BIOX process, but I'll also discuss using the BIOX process for the processing of base metal sulphides, as well as the high-tech process and the Aster process. Within the BIOX process, we'll look at an overview of the process, some technology details. We'll walk through the BIOX references. Then we'll look at the typical project development framework, the steps that you go through in development of a BIOX process. We'll quickly look at the capital and operating cost breakdown of a typical plant. And then, like I said, we'll quickly look at the mesotherm circuit, a recent addition to the BIOX process. So just to put the process into perspective, where it fits into the typical gold flow sheet, this shows the typical steps during the processing of a gold ore. You'll have crushing, milling, and thickening, with or without ore sorting and gravity concentration. After thickening, a free milling ore will go directly to the leaching circuit, followed by gold recovery. But for a refractory ore body, you'll normally have flotation and then an oxidation process, which is typically either pressure oxidation, roasting, or then bioxidation, the topic for the talk today. The BIOX product will then go to the standard leaching section for gold recovery. The high-tech process we'll discuss later. It's a process that's treating the CIL tails to mitigate perk robbing, and the ASTER process is a detox technology for cyanide extraction. So bioxidation is a biohydrometallurgical process for the pre-cyanidation treatment of refractory gold concentrates and includes tank leaching and heap leaching. The BIOX process is the proprietary process using stirred tank reactors, and all rights to this process is owned by Metso Outotec. As you can see in the first picture there, the gold particle totally occluded within the sulphide matrix. The BIOX process is then used to liberate this particle and expose it to cyanide for subsequent gold recovery. The technology has been commercially available for over 30 years. In that time, we've commissioned 13 BIOX plants in 7 countries, with 1 new plant currently under construction. Total gold production from BIOX over the years have been over 30 million ounces. It is quite a versatile technology in that it can be used at high altitudes. The highest BIOX plant currently is the Coricancha plant at over 3,000 meters above sea level. It can be used in tropical and arid regions, and it can operate in temperatures from -40 to +45. Operating plant sizes ranges from 20 ton per day up to 2,000 ton per day. And it's really a simple and effective oxidation process for metal liberation, requiring a relatively low skill set. This shows the typical flow sheet for BIOX process. The heart of the process is the BIOX reactors. We normally use a 3-3 or 4-4 configuration, meaning you've got 4 primary reactors in parallel, overflowing into 4 secondary reactors in series. Typical retention time in the BIOX process is between 4 and 6 days. Nutrients in the form of a fertilizer type, nitrogen, potassium, and phosphorus is added to the feed to the BIOX process, as well as dilution water to feed the process at 20% solids. The important engineering requirements during the BIOX process is the cooling of the process, and we do this using internal cooling coils as well as evaporative cooling towers, and the supply of low pressure air to supply oxygen for the oxidation process. The process will normally operate at 40 degrees Celsius. The materials of construction for the BIOX reactors is typically stainless steel, although mild steel rubber-lined reactors can also be used. During the BIOX process, the iron, sulfur, and arsenic is solubilized during the oxidation of the sulphide minerals. So following BIOX, a 3-stage CCD circuit is used to wash the BIOX product and ensure that you've got a clean oxidized solid slurry that is then fed to a standard CIL circuit. The dissolved iron, arsenic, and sulfur that is now in an acidic solution is neutralized in a 2-stage process using limestone and lime to produce stable ferric arsenate precipitates that can be deposited onto a tailings dam. As you can see, the process is simple and uses standard equipment, atmospheric reactors and thickeners for the process. The 3 important oxidation reactions for pyrite, acinopyrite, and pyrrhotite is shown here. Important to note is the high oxygen demand during the oxidation of sulphide minerals. It's also important to note that pyrite oxidation produces acid, while acinopyrite and pyrrhotite oxidation consumes acid. And this, along with the carbonate content in the concentrate, will determine whether the process is net acid consuming or net acid producing during bioxidation. This picture at the bottom shows the typical leaching mechanism during bioxidation. The bacteria do not actually oxidize the metal sulfide directly, but the bacteria will just regenerate the ferric that is the oxidant for the leaching of the metal sulfide. You'll typically have two types of bacteria in your tank, your iron oxidizers and your sulfur oxidizers. Elemental sulfur is oxidized all the way to sulfate. It is important to note that you will always also need a small amount of carbon in the form of CO2 for biomass production during bioxidation. This is normally supplied through the solution of carbonate minerals in the concentrate. Other important reactions during bioxidation is ferrous and elemental sulfur oxidation. Ferrous is for the regeneration of the ferric, that's the oxidizing agent, and elemental sulfur to produce sulfuric acid. As you can see, the reactions for the oxidation of copper sulfide minerals is fairly similar to the standard pyrite and acinopyrite. And that's why the process can also be used for copper sulfide oxidation. There's a few general precipitation reactions that will also take place either in the BIOX reactors or following BIOX during the neutralization step. The most important one being the precipitation of arsenic in the form of ferric arsenate, as well as the precipitation of iron and the remaining sulfides as the basic metal sulfide and gypsum. The most important process requirements during bioxidation is to maintain a steady temperature in the BIOX process, to control the pH, and to ensure a steady oxygen supply for the oxidation reactions. The BIOX bacteria can operate in a range of 30 to 45 degrees. However, we normally control the process within a very narrow range of 40 to 42 degrees. The reaction heat during bioxidation is relatively high, and the design of the cooling circuit is an important engineering criteria. The process operates also at a very acidic pH of 1.1 to 1.6, and that is normally controlled using either limestone and lime for an acid producing concentrate or sulfuric acid for an acid consuming concentrate. As I said before, the sulfide mineralogy and the carbonate content of the concentrate will determine whether it's acid consuming or acid producing. Probably the biggest operating cost and engineering requirement during the operation and design of a BIOX tank is the supply of oxygen. You require in the order of 2 kilograms of oxygen per kilogram of sulfur oxidized. And as we are supplying the oxygen in the form of low pressure air, it will mean that a large volume of air is pumped into the reactors. And the agitator needs to be able to disperse that air and also drive the oxygen mass transfer from the gas phase through the liquid phase to the mineral sulfide interface. Another important aspect of bioxidation is the fixation of arsenic following bioxidation to ensure that they have environmentally compliant products. We use a two-stage neutralization process using limestone and lime to produce ferric arsenate as the arsenic precipitate. And this has been shown to be a stable form of arsenic and conforms to the US EPA standards for the disposal of arsenic-bearing material. Typical results from neutralization tests during bioxidation is shown in the table, and as you can see, the solution concentration of both iron and arsenic following neutralization is well below the standard, as well as the TCLP or toxicity characteristic leaching procedure extract following treatment of the precipitate. The BIOX culture consists of a mixed population of a large number of microorganisms. These are all naturally occurring bacteria and can be found anywhere where you have acid mine drainage. We have just taken those bacteria and trained them up a bit to be able to operate at higher solids concentrations as well as higher temperatures, giving you faster reaction kinetics. We do not actually control the population of the bacteria, but we allow it to reach its natural equilibrium, and the dominant species will be determined by the process conditions as well as the concentrate characteristics. Interesting to note the concentration of bacterial cells per milliliter, and for a healthy population, the concentrations will be in the order of 10 to the 8 cells per milliliter. The bacteria are present as both free-floating as well as attached to the sulphides in the slurry. It's important also to note that the bacteria are non-pathogenic, and therefore it does not pose a risk to humans or animals. But it must be noted that the slurry itself contains dissolved iron, arsenic, and sulfur at a very low pH, so the slurry itself is toxic for humans. This slide shows the BIOX references, or some of the BIOX references that is currently either in care and maintenance or still in operation. The technology was initially implemented at the Fairview Mine in South Africa back in 1986. But the big breakthrough for the technology was with the commissioning of the Obuasi plant in Ghana. As you can see, a much larger plant demonstrating the scalability of the process as well as the operation of the process at a remote location. Currently, we are treating concentrates with a very wide variation in sulfur grades on the operating plants. The largest BIOX plant currently is the Cobalt plant in Uzbekistan, treating just over 2,000 tonnes per day of concentrate. And the newest BIOX plant will be the Cameron motor plant in Zimbabwe that is currently under construction. This plant will be implemented in 2 phases with a capacity of 100 tonnes per day for phase 1, doubling to 200 tonnes per day as part of phase 2. As I said, the technology was initially developed at the Fairview BIOX plant in South Africa. This was an old Edwards roasters that needed to be replaced. And it was the Gencore, and the mine was owned by the Gencore company in South Africa at the time. They evaluated quite a few different technologies at the time, and finally selected BIOX due to the lower, decided to develop the BIOX process due to the lower capital cost associated with the process. They didn't want to use roasting again due to the presence of arsenic in the concentrate, and the plant was too small for an autoclave. The plant is still in operation today, and CIR recoveries on this plant typically is in order of 98 to 99% following bioxidation. As I said, the largest BIOX plant in operation is the Cobalt plant in Uzbekistan. The first phase was commissioned in 2009 and the second phase in 2011. The plant demonstrates the ability to increase the capacity through the use of modules. The plant consists of 4 modules of 6 reactors per phase. The Coppertails plant will also operate, will see temperatures of +50 in the summertime and needs to operate at -20 degrees during winter time. The first application of the BIOX technology in really sub-zero conditions was the Sustal plant in Kazakhstan. The plant was commissioned in 2005 with a capacity of 160 tonnes per day of concentrate and expanded in 2010 to the current capacity of 520 tonnes per day. Being northern Kazakhstan, the plant sees -45 ambient temperatures for extended periods during winter. On the photograph, you can see the first phase or the first BIOX expansion on the right and the second phase then on the left. As you can see, the BIOX reactors are actually outside the building with the rest of the plant located inside the building. And there's only covered walkways on top of the reactors for running the piping, as well as to protect the operators from the extreme climates during winter. This shows a schematic diagram of the first phase at the Sustal BIOX plant. And again, as I indicated, the rest of the plant is located inside the building. Here showing the BIOX CCD, neutralization and water recovery thickener. And the flotation is then on the one side of the BIOX section and the CIL section on the other side of the BIOX section, with the BIOX reactors on the outside of the building with just a covered walkway. Also shown here are the BIOX blowers as well as the cooling towers. It's interesting to note that even during the coldest periods during winter with -45 ambient temperatures, you still need to cool the BIOX primary reactors, and the cooling towers are in operation throughout winter. However, designing the plant under these conditions is more difficult than a normal plant, and you need to take into consideration maintenance schedules and standby power procedures should there be a power failure during the winter. The Fosterville plant in Australia was commissioned in 2005 and it's a design capacity of 211 tonnes per day of concentrate at 20% sulfur. It's interesting to note that this plant sees elevated chloride levels in the processed water and had to be constructed from duplex stainless steel for that reason. The plant also sees elevated antimony levels in the concentrate. Normal operating levels range between 3 and 5% antimony, but they can see up to 9% in the concentrate without affecting the BIOX performance. The Coricancha plant in Peru was commissioned in 1998, but unfortunately only operated for a couple of years and is currently in care and maintenance. But the important aspects of the plant is that it operated at arsenic levels in the concentrate feed of up to 20%. And the plant is also located at 3,000 meters above sea level. Now again, bacteria does not really see the altitude or the external environment, but the high altitude does make the design of the aeration circuit more complex. The Ranrana plant in the Philippines was commissioned in 2016. And again, the design of the cooling circuit for this plant was very important due to high humidity and high wet bulb temperatures experienced in the Philippines. The plant also includes our latest generation 4 BIOX agitators, which is the higher efficiency agitators recently developed. The newest BIOX plant currently under construction is located in Zimbabwe near the town of Kadoma. It's an operating mine treating an oxide ore through a standard mill and CIL plant. However, they are running out of the oxide material and therefore decided to expand the plant to include a sulphide treatment plant, with BIOX selected as the oxidation process. The phase 1 plant will have a design capacity of 100 tonnes per day at 20% sulfur. However, when we did the design, we already designed the plant for the full capacity with only a full capacity of 200 tonnes per day, with only a part of the plant installed during phase 1. So for phase 1, we will install only 3 of the 6 BIOX reactors, 2 of the CCD thickeners, and 3 of the neutralization tanks, as well as the associated services and reagent makeup. And this will give us sufficient capacity for the phase 1 operation. Phase 1 is currently under construction and commissioning is scheduled for early next year. The plant will also include an ester plant using some redundant equipment for thiocyanate destruction. Phase 2 will then expand the capacity to 200 tonnes per day of concentrate with the addition of 3 additional BIOX reactors, 1 additional CCD thickener, 3 neutralization tanks. Additional blower and cooling capacity will also be added as part of the expansion. And here you can see a fairly recent photograph of the construction site showing the 3 BIOX tanks with the BIOX stock tank, the 2 CCD thickeners and the 3 neutralization tanks, as well as some water tanks and the tailings thickener. This is just a photograph showing the inside of the BIOX tanks, showing the BIOX agitators, which is the Metso Outotec Octop 3105 agitator, as well as the cooling coils used for cooling in the BIOX tanks and the sparge ring. And this photograph just shows the BIOX bacterial inoculum. We have already started the inoculum build-up process in anticipation of the commissioning of the plant early next year. So the inoculum is already on site and active. Just to give a bit of detail of the typical inoculum build-up process during the commissioning of a BIOX plant. We will typically take 10 liters of bacterial culture already adapted to the specific concentrate to site, and then use a number of reactors to step up or increase the volume of this inoculum to the point where you can commission the first BIOX primary tank. We will normally use a 10, 100 and 1000 liter laboratory reactor, followed by the nutrient makeup tank, as well as the neutralization tank that will be temporarily converted into BIOX tanks to increase the volume until you are ready to go into the primary tank. This process will typically be started in order of 4 months before you want to commission the first primary tank. And this time will also be used to train the operators to control the process. Now this slide shows the typical steps a BIOX project will go through during development of the project. The first state of test is called batch amenability test, and it's a series of batch BIOX tests on a concentrate sample. The tests are then stopped after different times to give the oxidation profile as well as the correlation between sulfide oxidation and gold recovery. The test normally takes about 3 to 5 months to complete and can be completed either at SGS in Canada, SGS South Africa, or ALS in Perth. Usually, in conjunction or just following batch amenability tests is a pre-feasibility study to determine the capital and operating costs associated with the BIOX project. This normally takes about 2 months to complete and can be done either in-house by Metso Outotec or with an engineering company. If BIOX is then selected as the preferred oxidation process for the project, we will conduct a continuous BIOX pilot plant run. This is normally done either at a commercial laboratory again, as well as at the actual mine site. We've got 2 standard pilot plant sizes, requiring about 150 or 650 kilograms of concentrate. Both plants will give exactly the same results. It will just depend on the amount of concentrate that is available for test work. Following the pilot plant run, we'll proceed into process design development and definitive feasibility study. During definitive feasibility study, Metso Outotec can give assistance in process design and basic engineering, as well as CapEx and OpEx cost development and hazard and risk assessments. We will then stay involved in the process during design, construction, as well as commissioning. We will approve the construction plan for the commercial plant, as well as prepare the operating manuals and training manuals during commissioning. As I also said, we will supply the bacteria and inoculum and be on site during the commissioning. An important part of the process is post-commissioning assistance. So that's ongoing technical support, structured process of plant optimization, and our BIOX users group. Like I said, the first set of tests during the development of a project is the batch amenability tests. This photo shows the typical batch amenability test and shows the simplicity of the process. It is really just a set of standard laboratory reactors that is stopped after different reacting times to give you the correlation of sulphide oxidation with bioxidation period. Typical batch bioxidation periods is much longer than the corresponding continuous retention time required on a commercial plant due to the mechanism of a batch test. In a typical batch test, you'll start with a large volume of inactive concentrate slurry, and you'll add to that a small volume of active bacterial inoculum. And it will take time for this small volume of active inoculum to multiply and to become active to oxidize the test. And from there, the much slower oxidation kinetics of a batch test. The batch amenability test program will give you typically sufficient information for the pre-feasibility level study, including the rate and extent of oxidation, the goal to solution as a function of oxidation, your order of magnitude reagent consumptions, and the neutralization performance, confirming that they'll produce stable arsenic precipitates, as well as settling characteristics for thickener design. The second step is then the continuous pilot plant operation. And this includes the full downstream testing, indicating the leach CL test work, as well as liquid solid separation, neutralization, and testing the properties of the different process slurries. The product from the pilot plant is a comprehensive report to BFS level, including the process design parameters, the process performance, reagent consumptions, and importantly, the operating philosophy during the operation of the BIOX plant. And this is the important graph that will be generated during a continuous pilot plant, and that will give you the sulphide oxidation as a function of retention time, and this will give you an operating window which we will use to design the commercial plant. Now, looking at the capital cost structure for a typical BIOX plant, you'll see the capital is a strong function of the sulphide oxidation tonnage into the BIOX plant. And that is simply because the two main cost drivers for the plant is the supplying of oxygen for the process as well as the removing of heat. Typically, the BIOX tanks and the BIOX agitators will make up 40 to 60% of the capital cost of a BIOX plant. CCD thickeners will be 10 to 15%, the blowers 10 to 15%, and the cooling towers and cooling water pumps 5 to 10%. The two main operating cost drivers for a BIOX plant is the power as well as the reagent costs, which is again dominated by the limestone and lime for neutralization. We've developed a high-level design program that will indicate reagent and power consumptions even at a very early stage during the development of the project, and that will help us to optimize the project and reduce the operating costs. Obviously very important is the availability of reagents and the cost of the reagents, as it's a main driver of the overall operating costs. Now, a little bit about the development of the technology over the years. What we call our Generation 1 and Generation 2 BIOX plants, commissioned from between the period of 1986 to 2010, is typified by the traditional or classic BIOX design. During this period, we proved that the BIOX design is sound, and we've got established testing design and commissioning procedures. However, during this period, we saw that there were still a number of factors affecting the performance of the BIOX process. These included some mechanical failures, especially on the BIOX agitators, some maintenance issues, and some process control issues. We then decided to launch what's called our BIOX Generation 3 design, and in this design we addressed these factors that affect the performance of the BIOX process. So we increased the robustness of the process through adapting our BIOX design program. We improved our service offering to improve the process control during operation, and improved our knowledge base and the application of this knowledge during commercial operation. We also attended to some main problem areas, including BIOX frothing, our sparge ring design to prevent blockages of the sparge ring, addressing some CCD1 gold losses, and very importantly, we addressed the agitator failures that we're seeing on some of the plants. And then following that, we decided to develop our Generation 4 design, BIOX design, and there we focused on achieving a 10% reduction in capital and operating costs. And this was through addressing the major capital cost items for the tanks, looking at materials of construction. Can we use alternative materials or alternative stainless steel grades? This development of the improved or more efficient BIOX agitators, and developing a more improved aeration control system, controlling the BIOX blowers. And in terms of operating cost, then that is addressing the power cost as well as reagent costs. This led to the development of the mesotherm circuit. Now what this is a combination of our standard BIOX bacteria operating at 40 degrees for the primary oxidation stage, followed by a secondary or high temperature thermophile stage to complete the oxidation. The advantage of this process is for the primary stage, we target between 60 and 75% oxidation. And the BIOX technology is a very well-known technology. The microorganisms are very robust, and we've got very well-known and defined operating parameters. The secondary oxidation stage or thermophile stage will then give us complete oxidation of the sulphide, any intermediate sulfur species in the BIOX product. You will have lower utility requirements at a higher temperature, but it is a more complex design, especially in terms of materials of construction. We also include an interstage thickening step to manage the dissolved iron and sulfate levels in the feed to the thermophile stage. And what we're trying to achieve is to reduce or eliminate any intermediate sulfur species that can be typically found in a mesophile BIOX product. These intermediate or partially oxidized sulfur species can react with cyanide to form thiocyanate and therefore increase your overall cyanide consumption. If we look at a typical Fairview ore sample that we treated using mesophile and then mesotherm, for the mesophile product to achieve good gold recovery, we required 19 kilogram per ton cyanide addition, with about 92% of the cyanide lost to the formation of thiocyanate and only a very small amount of cyanide still available for leaching at the end of the test. Where for the mesotherm product, to achieve the same level of gold recovery, we only needed 8 kilogram per ton of cyanide, with only 22% of the cyanide reporting as thiocyanate, and the bulk of the cyanide still available as free cyanide. So this was really developed to address one of the main operating costs for BIOX plant being cyanide. The process was developed through a toll-gated program to demonstrate it at various scales, and the various scales was then used to confirm our testing and design procedures. Some of the stages are shown here. 135 liter pilot plant and 1,000 liter pilot plant that was run at the Fairview Mine in South Africa, followed by a 21 cubic meter demonstration tank. And in 2019, we commissioned the first commercial reactor, which is one of the Fairview secondary reactors that was converted into a thermophile and now called a tertiary reactor. Now, this toll-gated process really confirmed the results of the process at different sizes and confirmed our design procedures. Okay, Ken, maybe it's a good time now to take a few questions before we go into base metal sulfide bioxidation. Jim, are there any questions yet?
I don't see any questions. I actually have a couple questions. It sounds from what you were describing that the pyrite concentration in the ore is very important, that it determines if the ore is acid producing or acid consuming in the BIOX process. Is there a key concentration of pyrite in the ore where you move from this acid producing to acid consuming regime?
Yeah, Ken, you'll have to determine that for every concentrate. As I said, it's both the sulfur mineralogy as well as the carbonate concentration that will determine whether the concentrate is acid producing or acid consuming. Now, normally you don't really have much control over that in the process. because you have to continue to concentrate that you're given. But we do see that most concentrates are acid producing, so requiring lime or limestone to neutralize or maintain the pH.
Okay, so then most of the ores have a reasonably high pyrite concentration.
Yeah.
Pyrite being very common. So that's what's typically the case.
Yeah, and that's normally where you would like to be, because it's just cheaper to add limestone compared to sulfuric acid.
Right. Yes. Well, sulfuric acid would be the more expensive choice, wouldn't it?
Yeah.
Limestone
Definitely.
being cheaper.
Yeah.
Right. Okay. Greg Romaine has a question here, and I'll read his question. What is the typical capital and operating cost difference between POX, pressure oxidation, and BIOX?
That's a very interesting question. I would say normally at the smaller plant scale sizes, you'd see that BIOX will have the capital cost advantage. And I think that is because of the simplicity of the process. You're really talking about aerated atmospheric tanks compared to an autoclave that is a fairly complex and highly instrumented piece of equipment. So typically for very small plants, we can see that the BIOX capital cost can be up to half the pressure oxidation capital cost. However, as you then go bigger, and we see that the switchover point is around about somewhere between 1,000 and 2,000 ton per day of concentrate. That is where the pressure oxidation capital cost will become more competitive. And that's simply because at one stage you reach the maximum size of a single BIOX reactor or BIOX module, and then you just start to add more and more modules. Whereas for pressure oxidation, you then get that economy of scale. Does that answer the question?
That makes sense to me. Greg, does that make sense to you? Yeah. I have one more question before we go on. So it sounds like the BIOX process is, yes, Greg says yes, thank you.
Yeah.
The BIOX process is an exothermic reaction. I guess it really comes down to those bacteria are living on converting from Fe2 plus to Fe3 plus, from ferrous to ferric. And that is an exothermic reaction, and that's where all the heat comes from, right? Is that the essence of it? So then it sounds like it might be actually easier to do this process in colder climates. Is it less expensive to, let's say, operate a BIOX plant in Canada versus operating it in, Ghana or Australia or something like that?
Yeah, now in terms of designing the cooling circuit, there's definite advantages operating in the colder climates. Designing the cooling circuit for high humidity, high wet bulb temperature environment is more difficult. However, saying that, I must say designing a plant for sub-zero and the minus 45 degree ambient temperatures does bring its own challenges as well. But certainly from a purely a cooling point of view, yeah, definitely much better in the cooler climates than the warmer climates.
So what are the challenges at operating at, minus 40, minus 50, that range?
Because your BIOX tanks are located outside of the building, typically you just have to ensure that all the utilities, so your cooling water pipes and nutrient addition and concentrate feed pipes are within a covered walkway or insulated somehow so that they don't freeze up at the very cold climates. And as I said, it's important also to have the standby power available and procedures associated with standby power available if you have a power failure or a plant stoppage at the very cold climates. You've got only a limited window to get the plant going again, or you'll see really the temperature starting to drop very quickly in those tanks.
So for people who live in Canada, they know that when the power goes out and the temperature in your house goes down, go down to the basement and open a tap and keep the water running through your pipes so it doesn't freeze up. It's basically the same problem, right?
Yeah. So we normally ensure that there's sufficient standby power, and we will develop a whole set of procedures for every plant, depending on the specific situation of what needs to be done immediately when there's a power failure, after a certain period, etc. So, yeah.
Okay. Are there any other questions? Okay, Jan, do you want to keep going on to the next section in your presentation, please?
Yep. It's quick thing. Now, as I said, the BIOX process and the mesotherm process can also be used for the treatment of base metal sulphides to recover the copper or cobalt. If we look at typical copper mineralogies, your oxides will be leached using acid, so no real BIOX needed there. For your secondary sulphides, the cobalt, chalcocite, and bornite, you'll typically use your 40-degree or mesophyll BIOX bacteria. But then for the primary sulphides, so chalcopyrite, energite, you'll need the mesophyll in combination with the thermophile or the higher temperature bacteria. And the reason for that is simply because the chalcopyrite mostly passivates under mesophyll conditions at a lower temperature, and you'll only get a partial oxidation, and you really need a higher temperature to complete the oxidation. If you look at some published bioleaching results, this is for mesophyll oxidation, and as you can see, for your secondary coppers, you can get very high copper dissolution, but for your primary sulfide minerals, the oxidations are much lower. However, if we use your mesotherm process, and this is some results from test work that we've done on different concentrate samples with varying mineralogies, you can see at the higher temperatures you can get back to very high copper dissolutions. Now, the bioxidation of base metal sulphides is certainly not a new technology or new processes. The first example of that on commercial scale was the Kasisi Cobalt Company in Uganda that used it to treat cobalt ferrous pyrite concentrate. And this plant operated for a number of years very successfully. And then Alliance Copper, the BHP Codelco joint venture, also demonstrated the use of the thermophile bacteria for treating energite chalcopyrite concentrate at 75 degrees C. And this was done at the Chuquicamata mine in Chile. So it's certainly not new technology. It's, I think, relatively well proven in the industry, but just haven't found that wide application yet. As part of the development of the base metal bioxidation, we had to really look at the flow sheet development. For gold bioxidation, the flow sheet is fairly simple, but for base metals, it's a lot more complex because you have to look at the recycling of raffinate after copper SXEW, and you also need to look at managing solution concentrations, your solution chemistry throughout the process. So we've developed a number of HSC chemistry software models to assist us to model this process. And the objective is really to maximize the overall metal dissolution, to minimize reagent consumption, important to try and maintain as simple a process flow sheet as we can. But having said that, also to maintain versatility, because as you know, no concentrate stays exactly constant during operation, and you need to be able to adapt the process to cater for variations in the feed concentrate. Some of the considerations that need to be taken into consideration is the BIOX cultures do have metal toxicity limits, and these must be managed across the circuit. And you also look to use the dilute acid in the raffinate across the BIOX reactors to reduce the overall acid requirement if needed. And this is just an example of the typical flow sheet that we've developed for one of the projects. And it shows the complexity of the circuit. This is a copper gold ore, a copper gold concentrate. And it's also a concentrate containing primary copper minerals. So meaning that we use our mesotherm process. What you can see here is the mesophile circuit, typical mesophile reactors, followed by the thermophile circuit with solution removal in between to manage your solution chemistry. Following by oxidation, you've got your standard CCD circuit with the solids going into your CIL section, followed by detox and tailings management. And then your acidic solution from your CCDs is combined with the interstage solution, as well as any other raffinate recycles, and that is then directed to the SXEW circuit to recover the copper with, like I said, raffinate again recycled either to your thermophile or your mesophile circuit, or even if you've got an acid pre-leach, it can be used there as well. So yeah, the circuit for copper does become a lot more complex, but we can model it very efficiently using HCC chemistry. And this is just a few photographs of a test program we did for a client of ours. They asked us to test their concentrate for copper recovery, but they also asked us during the process to actually produce a small copper cathode. Yeah, we followed the process and did each step of the process. Some of the results was very pleasing. We achieved a copper dissolution of 99.5%, cobalt of 96, and gold of 95, just under 95. So it really demonstrated the process, and it showed that there's no real fatal flaws in the process. Yeah, a really, really nice set of results. Next process I'd quickly like to touch on is the high-tech process. Like I said, this is a chemical process. It's not a biological process, it's a chemical process for the treatment of CIL tailings to recover preg-robbed gold. And in this process, we basically utilize temperature and solution chemistry, or through the addition of caustic, to dissolve gold from preg-robbed carbon in the ore. And this dissolved gold is then captured on fresh activated carbon. The process has been trialed, implemented, and is successfully being operated on 2 sites. And Metso Outotec acquired the technology actually from Curtin Lake that developed the process for the Fairview Mine in Australia. Just to show the flow sheet and briefly, so you will treat your standard CIL tails in firstly a desorption stage, normally consisting of 3 tanks. And this is where the temperature is increased and sodium hydroxide is added to dissolve, like I said, the gold that was absorbed onto the natural carbon and put it back in solution. And at desorption stage is then followed by an adsorption stage where the temperature is lowered again and fresh activated carbon is added to the circuit to absorb this dissolved gold or redissolved gold and make it available for recovery again. An important part of the design of the process is the energy management to manage the operating cost for the process. To test a new concentrate, we typically use small scale, that's 2 to 5 liter laboratory tests. These can be done in any commercial laboratory, or it can also be done at the mine site, like we've done for the Kazakhstan and Australian projects. And the pre-cropped sample is subject to different temperatures, and the gold desorption is then tracked at the different temperatures. We've then used a predictive model that we've developed, as well as high-tech fundamentals, to develop the design basis for the commercial plant. Rates of desorption and absorption is determined during the test work, allows us to do the process design, and the scale up from batch to commercial scale is now well established based on the Fosterville and Soestal high-tech validation. So like I said, the process was developed by the Fosterville mine in Australia. They implemented the first their plant in 2010, and the plant treats a combination of fresh CIL tails as well as all tailings recovered from the tailings storage facility. Now, Fosterville experienced quite severe preg robbing based on some black shale material that they can get in their concentrate. They've evaluated all the standard processes to try and mitigate this preg robbing, including blinding agents, as well as to try and remove the organic carbon before treatment using flotation or gravity, but nothing really addressed the situation or was associated with too high gold losses. So then they decided and they developed the process themselves following quite an extensive process of batch and continuous testing. But really the process is achieving very consistent results, matching and or exceeding their design. And they can get a 10% increase in overall gold recovery from the high-tech process. The second installation was in the Soestal plant in Kazakhstan. And they decided to install the process after a structured process of batch work that was done on site by them and then backed by a feasibility study. The plant was commissioned in 2016 and again treats a combination of fresh CIL tails as well as all tailings recovered from the tailings storage facility. And they can see an increase of between 6 and 8% overall gold recovery due to the addition of the high-tech process to their circuit. The last process that I'd like to briefly touch on is our Aster process. Now, Aster is a biological process for thiocyanate destruction in either a solution or a slurry. It's really a low capital and operating cost process, and we had to develop it because of the increasingly stringent requirements for the disposal of cyanide or specifically thiocyanate and the water management requirements around the BIOX plant. Standard cyanide destruction is relatively easy using chemicals, but thiocyanate destruction chemically is very expensive and often not that easy. And BIOX bacteria are very sensitive to any cyanides, including thiocyanates, in the water. So in order for our BIOX lines to be able to close their water circuit, we had to develop a process that can address the thiocyanate. The process is fairly simple. It normally consists of 1 or 2 stages of aster tanks, followed by a settler that can be included if required by the process. Typical operating conditions is somewhere between 20 and 28 degrees C, neutral or slightly alkaline conditions, and hydraulic retention times of between 12 and 30 hours. Mild agitation is normally included in the reactors themselves, and a low volume of low pressure air is added just to maintain oxidizing conditions in the aster tanks. The first commercialization of the technology was at the Consort plant in South Africa. Now, this is one of the plants that produces the concentrate that's treated at the Fairview BIOX plant, and therefore no cyanide or thiocyanate can be tolerated in the process water for the Consort plant. So the aster was installed to treat tailings dam solution and allow recycling of this solution then upstream to the flotation section. It's a relatively small plant, treating only about 320 cubic meters per day of solution at relatively low feed thiocyanate concentrations, but achieving very good results. And it really showed the simplicity of the process. These are just plastic water tanks, JoJo tanks, that are fitted with a sparge ring at the bottom, and overflow and feed pipes. And that is really the aster process or aster tanks for the Consort plant. The second installation was in the Sustal aster plant in Kazakhstan, and they retrofitted current redundant tanks in the plant and repurposed them to be used as the aster tanks. They treat thiocyanate concentrations, or they have treated thiocyanate concentrations as high as 3,500 ppm. And again, the solution from the aster is then recycled upstream of the BIOX. Typical operating results are shown in the table, and as you can see, the actual thiocyanate feed, and this is the average of the operation to date, is in the order of 2,400 ppm, and again the results in the aster product is less than 1 ppm thiocyanate. The third application was the Randrano plant in the Philippines, and this is by far the largest aster plant to date. And this is also the first plant where we had to treat a dilute slurry. This is because of the requirement for Randrano to detoxify the solution prior to discharge onto the tailings dam. So as you can see on this graph, you've got your standard CIL, and this is followed by a cyanide detox step using standard SO2 air. And the cyanide detox product is then diluted to be up to the design of 4.5% solids, but periodically it goes up to 10% solids for the aster section. So the treatment rate for Randrano is quite high at 5,000 cubic meters per day, but again at relatively low thiocyanate concentrations due to the dilution. but again, achieving very consistent results. And this water is again then pumped up to the tailing storage facility, and overflow water is returned to the process. And the latest aster plant is the Fosterville plant in Australia. And here the aster really enables reuse of the detoxified solution, again in the BIOX circuit, and they treat the highest thiocyanate feed levels to date. They see up to 5,000 ppm thiocyanate in their feed, and the target is to achieve below 1 ppm. This plant was commissioned earlier this year, so we're just still gathering the operating data, but so far operating very well. And Jim, that is the end of my presentation. If anybody needs any further information, feel free to ask now, or you can contact me afterwards. That's my contact details.
Okay, does anyone have any questions? Okay, I've been jotting down a few questions here. Really elementary one. I'm not familiar with thiocyanate. How dangerous is thiocyanate? Can evolve a poisonous gas like cyanide, or what are the dangers with thiocyanate?
No, it's actually a fairly stable compound, Jim. And the danger or the issue with thiocyanate is really the BIOX bacteria is fairly sensitive to thiocyanate, or any cyanides for that matter, in solution. So for our BIOX clients to be able to close their water circuit and return any cyanide or thiocyanate containing water, they had to detoxify it. And that's the reason why we developed the process. So it's really just to assist our BIOX clients to return water upstream of the BIOX.
So that the thiocyanate ions can kill the bacteria, is that it?
Yeah.
Okay. Speaking of bacteria, I once, it was actually courtesy of McEwen Mining. They actually, it's Rob McEwen himself who finances these lunches. He actually, actually, it's Nathan Stabina was working there at McEwen Mining at the time. He said there actually is a free lunch, and the free lunch is about 30 or 40 people get together at McEwen Mining's offices in Toronto, have a great lunch, and then they listen to people do some presentations. And one of these presentations was all about all the bacteria and all the creatures that live on the planet Earth. And there's, if you look at the sort of tree of life, shall we say, about 90% of it is all of these little creatures, not animals like we think about, but bacteria, etc. So there's just a huge number of these types of bacteria. Are there some out there that might be even more effective than what you're using? Or are you doing some research into finding, new and wonderful bacteria?
Short, not at the moment, Jim. From time to time, we do run programs to evaluate alternatives. And I think that's a typical example is the development of this thermophile or high temperature bacteria. Again, that's not new. Those are not new bacteria, but we developed the engineering around it for commercial application. But so I think at the universities, certainly there's a lot of development going on in terms of alternative bacteria to use. Thinking specifically there around the treatment of acid mine drainage and other wastewaters. There's development into the use of bacterial processes for sulfur reduction. So there's definitely a lot of other developments ongoing.
Okay. Okay, so Greg has come back with another question here. Thanks, Greg. Greg's question is, I have heard different opinions, but in your experience, is it more difficult to start up a pressure oxidation plant or a BIOX plant? So he's asking about the difference in startup difficulty.
Yeah. I think it will depend on the specific project, Greg. I've been involved in like the fossil commissioning went extremely well and was very easy. Some issues afterwards, but the commissioning process itself was very simple. But then we know not all commissionings go that easy. So I think the big difference is with the BIOX, we start the commissioning, like I said, we start the inoculum buildup, and that's probably 4 months before you actually commission the plant. We start that process in the laboratory as well. So it's a lot longer process. Whereas I think for an autoclave, you really wait till everything is constructed and then you start the commissioning process. So yeah, I think the difficulty will depend on the specific project, but I think the BIOX process, it's a longer process than an autoclave.
Okay, Jan, I have one more question. I was interested in, you gave the example of this process they were using at Chuquicamata in Chile, and they were operating a BIOX process to oxidize, I'm assuming, sulphide copper minerals at 75 C, which sounds pretty hot considering what you've been talking about. Were they using only these thermophile bacteria, or were they using some other type of bacteria?
No, they used only the thermophile bacteria. So that was a fully thermophile process. The thermophile bacteria we use are essentially the same. We just decided to use a combination mesophile thermophile bacteria or process, and that was in the mesophile process where we do the bulk of the oxidation. We're at a lower temperature, so the engineering requirements are slightly simpler, and there's still slightly more robust organisms. And then you follow that up with the thermophile stage when the engineering requirements are then more complex, but your duties are lower as you've done the bulk of the work already. So,
is there any advantage to only using thermophile bacteria and only operating at the higher temperature?
I think it will depend on the specific concentrate. If your sulfur grade is too low, then you'll probably look at only thermophiles. But yeah, the work we've done, certainly I think the combination process is the optimum for the...
So the optimum is to use both the mesophile and the thermophile.
Yeah, no, I think that's certainly what we've seen so far.
Okay, Greg has another question here. He says, can you talk a bit more about the skill set required to operate BIOX versus pressure oxidation?
Yeah, no, very good question. Something that I actually didn't address during my presentation. Yeah, the skill set required to operate a BIOX plant are actually fairly low. Common perception is that you need microbiologists on site and quite highly trained operators, but the opposite is actually true. None of the BIOX plants, and even in my BIOX group, we do not have any microbiologists. We normally use a commercial or one of the research facilities like University of Cape Town or one of the other microbiology research facilities if we need any microbial work to be done. So the actual control parameters that the operations used are simple ferrospheric titrations, redox measurement, and pH measurement to control the BIOX process. So it's a very simple process to manage, and your operators are typically somebody with matric or high school education, and they basically need to be able to read and write and take basic process measurements. and then yeah, it's only when those parameters go outside a standard range that the plant metallurgist or process engineer will become involved to assist with doing the fault finding and taking corrective actions. I think that is different to an autoclave where you really need relatively highly skilled operators as you're working at elevated temperature and pressure and really a lot more complex process control.
Any other questions? Maybe actually I may have asked one more that I sort of didn't quite understand. This high-tech process was developed at the Fosterville gold mine in Australia, and I'm sorry, I'm looking at the chat here. I just noticed a little red light turn on here. Well, we'll figure that out in a moment. Okay, the Fosterville plant, Fosterville mine in Australia, they had this preg robbing problem because there was carbon in the black shale, and then the gold ended up bonding with that carbon in the black shale, and then the process, the high-tech process with this. Well, actually, could you just go through again really simply? How is it that the gold is then extracted from this carbon in the black shale?
Yeah, so first of all, goes through the standard process. We've got BIOX to oxidize the sulfur, followed by standard CIL to recover the bulk of the gold. And this is where all the gold is solubilized or dissolved using cyanide, but then a portion of that gold goes and sits on the preg robbing material, the organic carbon, and that's then not recovered onto the activated carbon. So following CIL, the CIL tailings is then treated in the high-tech process, and there you manipulate temperature, so increase the temperature to between 60 and 80 degrees, and you add some caustic to just manipulate the conductivity or solution chemistry in the solution, and that it's like an elution process. You're essentially doing a gold elution just on a larger scale. So that by adding temperature and caustic, you're actually eluting the gold off the organic carbon back into solution. And then if you then add fresh activated carbon, it can compete for that gold and recover it.
So at that higher temperature, 60, 80 C, and the higher pH, because you've got this caustic solution, under those conditions, the gold sort of lets go of the carbon, and then what it bonds to forms a complex with cyanide?
Yeah, so there's still cyanide in the solution as well, being CIL tailings. Yeah, so there's still some cyanide, some caustic, so the gold goes back into solution, and then it's absorbed onto fresh activated carbon that you put into the circuit.
Okay, I must say that's clever. Because you're just sort of you're encouraging the gold to go from one carbon to another. That's
yeah. No, it actually, the process works amazingly well.
Any other questions? Okay, well, I think we'll wrap it up there. And John, I'm going to turn on my camera here because there's something I want to show you.
Yep. Okay.
So
stop sharing here.
See if you can see the picture here.
Bring it more towards your face, Jim.
Is that right?
Yeah. And up. It's just, it's your background is hiding it.
Oh, okay.
Maybe if you could change the background to your regular
Maybe I'll
background.
take my background off. Okay. Just give me a moment here.
Yeah, I think Greg just also sent a comment. Just to remind everybody that the Fosterville mine is now owned by Kirkland Lake Gold, and they're merging with Agnico Eagle. So yeah, with all the refractory gold in northeastern Ontario and Canada for that matter, yeah, there's a good chance that you'll hopefully see a BIOX plant in Canada soon.
Okay. Yeah. That'd be interesting.
Yeah.
So anyway, this is what I'm trying to show you. There we are.
The lighting
Yep.
doesn't show its true beauty though.
Well, it's close.
Yeah.
Okay. So anyway, this is a token of our appreciation at the Haileybury School of Mines. And this is for you, Jan. Thanks very much for this very interesting lecture. I learned a lot. And what this is a painting of the head frame of the townsite mine in Cobalt, Ontario. So a little of the history here, which is connected with what we're talking about. Get the picture there right. Yeah, so in 1903, they found silver in Cobalt, Ontario. And there was a cobalt silver boom from 1903. And I think the mine's finally going into probably about the 1990s. So in that time, they extracted $20 billion worth of silver. There were 100 mines in this small town. It's only about 1,500 people now. And let's see if we can get that. There we are. And so about 1912, people said, well, we got 100 mines going. We need all these people who are trained to work in these mines. So they created the Haileybury School of Mines. And that's where the Haileybury School of Mines, where I work, that's where it came from. Curiously, actually, my family showed up in Cobalt in 1910, emigrating from England. And my great-grandfather actually ran the hoist at this particular mine. His name was Gartside, and he ran the hoist at the townsite mine from 1910 to 1939. In fact, he showed up in 1910. He wanted to be an underground miner, and they said, "You're too small, but you seem fairly smart, so you run the hoist." And that's how he got hired.
Okay, that's interesting.
So please send us an address where we can mail this to you, and with our thanks. And hopefully you can hang that on your wall and think of us when you look at it.
Yeah, no, thanks. Thank you very much, Jim. I'll definitely send you the address.
Yeah, well, thank you. So with that, we're going to oops, I'm gonna put this down. Sure, take good care of it. With that, I'm going to say thank you, Jan, for the very interesting lecture. And we're going to end our Haileybury School of Mines guest lecture right here. So I'd like to thank everyone for attending, for asking interesting questions. And I'd like to bid all of you a good night. Thanks very much.
Speak again.
Okay, bye now.